start over before 5 minutes consider with a constant multiplier and addition and stuff like that. Anyways, okay, let me go to the very last level, and then I will inshallah vectorize this implementation. By vectorization, I mean you do not need these subscripts and summations. Everything will be in matrices and products and this kind of stuff. Okay, and that will make much more sense. How to do a forward pass, how to do a backward pass. Other equations for forward pass, backward pass, and we will not know J, I, a lot of these subscripts will be gone. Okay. Okay. Now let me go to. By the way, remember to compute deltas, we need the delta at the very last layer, the last user. And remember the last layer on. It gives me, let's say the last layer is capital L, that's it. It outputs AL, which just called Y hat carry. Yes, इसी को Y hat carry, this is the last neuron. और मैं assume कर रहा हूँ last neuron पे, last layer पे एक ही neuron है, तो एक लेवल है neuron, ठीक. And this is the last layer. I want to compute delta L for the last layer. And this will give me the delta of the previous layer by this formula. Make sense? So let's compute delta for the last layer. So far, so good? Okay. I'm not erasing this. I may need this further, but I'm just using this. So this delta L, the last thing, this is actually partial EI or partial ZL. I'm not writing ZL subscript because there is only one node in the last layer. Yes, because that's a single label classifier, that's one label there. Binary classification. We'll see later in maybe the next lecture, inshallah, that you can achieve the multi-classification directly. In that case, you'll be having a softmax layer here, and you'll be having more than one node in the last layer. Achha. Right now, yeah, that is just a combination of binary classifiers using one versus the rest approach. But that's an easy implementation of neural networks. You can use that. Okay, this is equal to, by the way, ZL is here. ZL is here. This is equal to partial EI over partial AL, which is your Y hat, into partial AL over partial ZL. If you see this partial AL over ZL, this is simply G dash of ZL. Yes? Because this is G and this is, so derivative of G of ZL by ZL is just this. If you see this thing, this is differentiate this with respect to AL. Differentiate the error with respect to AL. And this is very simple. Your error, if you remember, is the following. This is your error, EI. मैं इसको y hat कह रहा था, अब ये AL है. अगर मैं इस function को differentiate करूँ with respect to this variable, ये क्या होगा? What is the derivative of this with respect to AL? L is not power, it is just a superscript. This is 2 times AL minus power. That's it.
That's it.
Yes? Okay. So into, I'm writing this 2 here, writing this 2 here, and then we have AL minus YI. This is your delta L. That's it. You are done. You found your delta L. You found delta at the last layer. आप सरप्राइजिंग आप खुशी आखिरी लेयर पर डेल्टा मिल गया यार. Okay. And here, if you have some other cost function and a square error, you will just plug in that derivative here. And you can come up with any cost function. Okay? At the very last layer, you take the derivative with respect, and this is just this part that will be affected. अगर देखें फॉरवर्ड पास में जब आप आए थे फॉरवर्ड पास में आपके पास ZL सेव था जब आप यहाँ पे कहीं पे इंटर हुए थे तो ZL आपने कंप्यूट किया था, दैट इज सेव्ड। AL आपका आउटपुट आई y हैट जिसको हम कह रहे थे, और y आई वो लेबल है जो ट्रेनिंग के दौरान हमने सप्लाई किया था कि ये जो एग्जांपल है इसका लेबल ये होना चाहिए। सो ये भी गिवन है, ये आप कंप्यूट कर चुके हैं, ये आप कंप्यूट कर चुके हैं। सो डेल्टा L इज कंप्लीटली कंप्यूटेड। यस, once delta L is computed, I will go to this formula and I will compute the deltas at the previous layer. Now in the previous layer I have all the ZJs. जब मैं फॉरवर्ड पास पे गया था तो हर एक नोड का ZJ I have saved and I have saved there. वो मैंने थ्रो नहीं किया, during the forward pass मैंने थ्रो नहीं किया there. I have all the Z's available, so I have the derivatives. I have all the W's available. जो start में मैंने weights initialize किए थे वो मैंने रखे हैं, जो इसलिए ये वाले weights हैं वो और delta L मुझे last layer से मिल गया होगा। Yes, so end up having this number multiplied by this number. I have this. All these, once I have all these, I plug in there. I have never thrown these away. ये मेरे पास computed पड़े हुए। So I have this update available now, and I have all the updates. Yes, sir? Yes. This is back propagation algorithm. Make sense? Yes, sir. Now I am going to vectorize this. By vectorize I mean I'm going to write this in a way that you understand much more concretely and you can implement very easily. Obviously यहाँ पे आपको sum नजर आ रहा है, recurring नजर आ रही है, loops, recurring का क्या business चल रहा है, so you can make it faster by vectorization. लेकिन अगर मैं आपको vectorize कोड ना बताऊं, you can still implement that propagation now. The idea is the following: given an input data, input point, initialize some weights, all the weights, initialize them and save them. Clear? Then throw your input through the first layer. That will compute all the Z's at the layer. Save the Z's. Then pass every Z through G. This will give you A's. Save the A's. Then pass those A's to the next layer. Compute the Z's and A's. Then to next and so on. Save everything. All the weights, all the Z's, all the A's. You need them when you go back.
Yes.
At the last layer, compute delta L through this formula. Plug in delta L back, compute delta L minus 1. For computing delta L minus 1, you need the previous weights, previous A's and Z's.
Yes.
Use them and compute. Once you have all the derivatives of weights, update a weight Wij L minus 1 is equal to Wij L minus 1 previous minus alpha so that is the number you have computed now. This is the old one. This is the number you have computed. So back propagation. This is a fixed number called learning rate. In practice, I will talk on this on the next lecture. The learning rate should be adaptive. As you move on, the learning rate should adapt itself rather than be a fixed number. We'll see that. But for now, this is the number. And through this formula, you have your new weight. Change all the weights. Okay? Then come up with another example. Change all the weights. Then come up with another example. Change all the weights and so on. So here is the algorithm. Pick one example. Forward pass, backward pass, change the weights. Pick another example, but for the next example, the previously learned weight, वहाँ से आपको शुरू करना है. For the very first example, you start the weight initialization as random. For the next example, the previous learned weights will serve. Make sense? So for the next example, the example number 2 in your data set. Forward pass, backward pass, update the weights. Then example number 3, forward pass, backward pass, and so on. Make sense? Once you have gone through all the training data points, one by one, this is called one epoch. You have done one epoch, one pass of your data. Say it? Then go and do another epoch. Then go and do another epoch. And go and do another epoch. And so on. G is the most common choice of G is I will talk on variants of G as C. The other G function is tan H, hyperbolic tangent. It has some better properties than this. And so far the best is value, which is, it is called rectified linear. G of x is equal to max 0 of x. So in दोनों में से जो max होगा, that is the output of this. और अगर आप देखें कि ये function कुछ इस तरह का है, it is 0 everywhere and it goes like this. It is linear but rectified linear. Clear? It is not differentiable at 0. The derivative in this area is 1. The derivative in this area is 0. It is not differentiable here. It is not bounded. It can give anything. But it turns out to have very good properties and very fast and rate. You'll see that. सही है जी? Okay. Now, if you are able to implement this in this way, I'm going to show you that it can be vectorized. Rather than computing each weight independently, we can compute all the weights of a node at once. I mean, by just not applying the loop explicitly, by achieving matrix multiplication. Make sense? Now I'll be erasing that code. That's okay. Should I erase that code?
Yes.
Okay, so this is layer L minus 1. I'm assuming 3 nodes in it. These are the weights of layer L minus 1. This is the weight 1. This is the weight 2. Layer L minus 1. This is the weight 3. L minus 1. That's a column vector I'm assuming. I mean, all the nodes coming in. For everyone there is a number here, okay? So the weight, I mean ये जितने भी nodes आ रहे हैं, उन सब के weights का एक vector column vector मैं उसको कह रहा हूँ. That's a weight vector of the node one. Weight vector of the node one. जो पीछे से इस पे input आ रही है, I'm calling that as A L minus 2. Because the same input is going there, and that's a vector now. There is no subscript here. That's a vector. And all the inputs that are coming in, that's a vector. Right? And Zj at L minus 1 is actually Wj L minus 1 transpose A L minus 2. Make sense?
Makes sense.
That's the forward pass. Or if you write all these, because all these W's, W1 has same number of elements, W2 has same number of elements. क्योंकि किसी एक नोड में जो number of inputs आ रही हैं, दूसरे नोड में भी उतनी आ रही हैं. They are all same. अगर मैं इन सबको एक बड़े मैट्रिक्स में लिखूं और वो बड़ा मैट्रिक्स ये हो, W1, so that we call it L minus 1. W1 L minus 1, that's a column. W2 L minus 1, that's a column, and Wn L minus 1 जितने इसके nodes हैं, L minus 1, that's a column. If I call this as W matrix, then W L minus 1 transpose times A L minus 2, it will give me Z L minus 1. So the first value, this is a vector now. The first value of Z is actually Z1. The second value here is Z2. The third value is Z3 and so on.
Yeah.
Make sense?
Yeah.
So that's the forward pass. So then we have A of L minus 1 that is equal to G of Z L minus 1. Obviously this function is applied element wise. This is a vector and this function is applied element wise. That's a forward pass, that's it. If you want to implement forward pass, that's it. I mean, initialize your A is 0 to be X input, initialize the weight matrix of each layer. Now each layer has a weight matrix, and then compute this by these matrix multiplications.
No.
So far so good?
Yes.
That's a thought pass, makes sense. I mean, just multiply these and you get it. Now, if you see, if I want to compute, I mean, Wi and J, Wi, then we have Wi. If I want to compute all the weights, if I want to compute all the weights of a jth node, obviously the jth node has a lot of weights. Let me call them Wj of L minus 1. All the weights of the jth node, okay, of layer. So, how will I compute? I will say, I'm just keeping these two equations. Can you erase the rest?
Yes.
Oh, by the way, this I and this I, they are not the same. That's an error in this I and this I should. This is the ith example, and this is the ith node. I should have used another value here. So please correct this. Okay. If I just I out, I pick this I out. Now this is a vector, column vector. That's a number, and it returns a column vector. The update of all the weights with respect to this weight vector.
अच्छा.
So पहले तो ये, so for example अगर ये I है और ये भी I है, so अगर मैं J को fix रखूँ, I को change करता रहूँ, so क्या होगा? अगली वैल्यू क्या आएगी? अगर मैं I को 1 लूँ तो यहाँ पे 1 आ जाएगा. अगर मैं I को 2 लूँ तो यहाँ पे 2 आएगा, यहाँ पे 2 आएगा, ये रह जाएगा. अगर मैं I को 3 लूँ, यहाँ पे 3 आएगा, यहाँ पे 3 आएगा, ये भी होगा. अगर मैं सबको एक वेक्टर की फॉर्म में लिखूं तो ये बनेगा a1 l minus 2 times sigma j l minus 1. अगर मैं ये वेक्टर को देखूं तो ये है जो i1 के लिहाज से अपडेट है. अगर मैं i की वैल्यू 2 कर दूंगा तो यहाँ पे आ जाएगा कि ये 2 l minus 2 and so on.
Yes.
And this vector can be achieved by having this L minus 2, which is the vector, this vector, that's a column vector, this column vector, times this scalar.
Yes.
And this is actually the derivative of error with respect to all the weights of J. That's a gradient with respect to all the weights of J.
Right.
Make sense? Now, अगर मैं J भी move कर दूँ J, तो ये J separate होना शुरू हो जाएगा J1 J. So for example, अगर मैं J1 रखूँ, एक नोड, J1 रखूँ तो ये आएगा. अगर J2 रखूँ, तो यहाँ पे कुछ ये वेक्टर सेम रहेगा, ये फर्क आएगा. Yes? अगर J3 रखूँ, ये वेक्टर सेम रहेगा, यहाँ पे स्केलर फर्क आ जाएगा. So actually different अगर मैं न्यूरॉन्स उठाऊँ, उनके वेट्स अगर मैं डेरिवेटिव लेना चाहूँ, तो this is the word that is actually changing. This is staying the same. Yes? So I can rewrite this as the following. The derivative of E with respect to the matrix at L minus 1, all the neurons, that is equal to A L minus 2 column, A L minus 2 column, so on, as many columns as there are neurons, times A1 L minus 1, sigma 2 L minus 1, sigma जितने neurons हैं. That's a diagonal matrix. If you multiply these two matrices together, the first vector will be scaled by this number, the second vector will be scaled by this number, the third vector, and the result will be this. Sigma 1 times A L minus 2, then sigma 2, A L minus 2, then sigma. That will be the vector. And these are the updates of all the metrics. So एक matrix आपके पास है, ये आपने updated निकाली है. Subtract the previous matrix minus alpha times this matrix. So you can update each vector है वो एक न्यूरॉन को वेक्टर करेगा. ये वाला नीचे ये लास्ट वन ये जो कॉलम है. Yes. So this is actually the एक single न्यूरॉन. Yes, this is the derivative with respect to the weights of one neuron. All of this. Yes. This is I have just rearranged this thing.
Yes.
Yes. Make sense? So
सही सिर्फ एक लेयर का भी है ना पर
ये अभी एक लेयर का है.
हाँ.
So that's why it is L minus L.
यही बार-बार करना पड़ेगा.
सही है. So हर लेयर के लिए ये फॉर्मूला लगेगा.
Yes.
If I call this matrix as A, and I call this matrix as diagonal of lambda L minus 1, will lambda L minus 1 contain all these numbers?
Yes.
Then the weight update is simply, so weight update is simply A times diagonal of lambda L minus 1. So you compute all the delta of L minus 1 and compute this A. A is just a copy of these vectors. Multiply them together, you have all the weight updates at once.
of one layer.
So yes, now you can update the weights of that layer.
Yes.
Clear is it?
बेहतरीन.
Similarly, you can vectorize this equation. So here I'm going to vectorize this equation. I'm going to erase that code now. That's okay. Yes? Okay, see this. This is simply a dot product, nothing else. This is a dot product.
Yes. ये सम है.
Make sense? This is a dot product. जिसको मैं लिख सकता हूँ actually, it is the jth row of matrix WL. Remember WL is what? WL was W1 of L, W2 of L, and so on. This is WL.
Yes.
JK means, because K is changing, J is fixed. This is the jth row of this matrix. Jth row of this matrix multiplied by this column vector. जिसको die form में मैंने यहाँ पे लिखा है. See this one, that one. These are real numbers. If I write all these real numbers, L minus 1, then that is that 1 L minus 1, 2 L minus 1, everything L minus 1. If this is a vector, इसको diagonal form में लिखे तो ये आता होगा. अगर diagonal form में ना लिखे as it is लिखते हैं, that's a vector. If this vector is multiplied by the jth row, that's this what is written here. Yes or no?
Yes.
If you see closely, it is the jth row times this column. And I can skip the key here. So this is this means the jth row. This means the jth row of this matrix multiplied by this L minus 1. K is out.
Yes.
K is out. Now this is a vector, this is a row. Let me make J out as well. This is dot static, pointwise multiplication. This is the whole matrix. So this WL is the matrix of all these W's. This is a column vector. You multiply, you end up with a column vector. Pointwise multiply this column vector with those. Because this ZL minus 1, it is a vector now. So जितना ही वेक्टर है एलिमेंट वाइज उसका डेरिवेटिव लेंगे तो इतने वेक्टर एलिमेंट्स आते हैं. डॉट स्टैटिक ये भी एक वेक्टर है. सो एक वेक्टर को एक वेक्टर के साथ एलिमेंट वाइज मल्टीप्लाई करेंगे एट द एंड आपको एक वेक्टर आएगा एंड दैट इज दिस वेक्टर. So see, everything is just, I mean, all that summation and stuff, this is like this.
डॉट वर्क डॉट वर्क हर एलिमेंट अलग चाहिए उस लेवल पे हर एक का डाटा अलग चाहिए. मल्टीप्लाई नहीं सर, वो मल्टीप्लाई तो नहीं है ना, आप डॉट अगर सब बात डॉट
So this is MATLAB notation for writing point-wise multiplication.
अच्छा ठीक है.
This is not matrix multiplication, this is point-wise multiplication, and this is MATLAB notation for that. यहाँ पे by the way, this is L minus 2, AL minus 2, and then we have this, and we have that. यहाँ पे okay, these two. And then the forward pass we know A of L, Z of L minus 1, this is actually W L transpose times A of L minus 2, then A of L minus 1 is equal to
G of
Z L minus 1. This is forward pass, this is backward pass. That's how we do it. If you have a matrix multiplication function available, you just call that function without loops in your layer by layer. You move layer by layer.
So you have to do one for loop.
Yes, on layers.
Yes.
On layers, yes. Explicit for loop. Implicit तो इसके अंदर भी यहाँ multiplication करोगे. Explicit for loop शायद है. और वो loop और इसके ऊपर एक और loop है जो हर example में आ रहा है.
Ah yes.
So there is a nested loop.
Yes.
Clear है जी?
Yes.
एक छोटी सी चीज़ और फिर मैं लेक्चर खत्म करता हूँ. आखिरी बात. ये जो बातें सारी मैंने अभी आपको बताई हैं अब तक, इसमें कोई डीप लर्निंग की बात नहीं. ये न्यूरल नेटवर्क्स हैं और बड़ी देर से इंट्रोड्यूस हुए. ये न्यूरल नेटवर्क्स हैं. बड़ी देर से ये अराउंड थे. न्यूरल नेटवर्क लोग काम कर रहे थे. बैक प्रोपेगेशन दुनिया जहाँ बहुत पहले का आ रही. डीप लर्निंग इज समथिंग that has changed the field by just doing certain steps in the neural network. Previously होता ये था कि आप layers multiple add करते हैं, different layers. It just so happens कि जो start वाली पहली layer है ना या दूसरी layer, उस पे जो derivatives हैं, updates, they are very small. और उसकी वजह क्या है वो भी मैं आपको बताऊँगा. This problem is called vanishing gradient. वैनिशिंग ग्रेडियंट ये है कि फर्स्ट लेयर जो है ना, एक्चुअली अगर आप गौर से देखें जो फर्स्ट लेयर पे डेरिवेटिव है, इट इज बिकॉज ऑफ रिकरिंग, इट इज प्रोडक्ट ऑफ अ लॉट ऑफ नंबर्स, एंड इफ several of these numbers are smaller than one, the product will become very small. If the update is very small, तो पहली लेयर का वेट अपडेट ज्यादा होगा नहीं. पहली लेयर का वेट अगर ज्यादा अपडेट नहीं होगा तो सब्सिक्वेंट लेयर्स के वेट्स अपडेट नहीं होने. लिहाजा आपका बहुत हैवी जो नेटवर्क था जिसमें लेयर्स बहुत ज़्यादा थी, इट एक्चुअली सर्व एज अ वन लेयर न्यूरल नेटवर्क. एंड दिस वाज अ प्रॉब्लम फॉर सो लॉन्ग इन न्यूरल नेटवर्क्स. वो कहते थे कि हम इतनी लेयर्स ऐड कर रहे हैं, लर्निंग इज नॉट हैपनिंग ड्यू टू दिस वैनिशिंग ग्रेडियंट प्रॉब्लम. एंड दिस डीप लर्निंग इज एक्चुअली हैज फिक्स्ड दिस प्रॉब्लम ऑफ वैनिशिंग ग्रेडियंट, एंड इट अलाउज सेवरल लेयर्स, ऑल द लेयर्स टू लर्न. And there this neural networks kind of reborn this one problem, vanishing gradient. और ये पहले इतनी ज़्यादा रिसोर्सेज भी नहीं थी और इतना ज़्यादा डेटा भी नहीं था कि इसको अनकवर भी किया जा सकता कि दिस इज द प्रॉब्लम दैट इज एक्चुअली हैपनिंग इनसाइड द वर्ल्ड. अब वैनिशिंग ग्रेडियंट को सॉल्व करने के लिए वेट इनिशियलाइजेशन की कुछ टेक्निक्स हैं, वो लोग यूज़ करते हैं. मैं आपको इंशाल्लाह नेक्स्ट लेक्चर में बताऊँगा. इसी को सॉल्व करने के लिए ये जो हर न्यूरॉन की आउटपुट है उसको एक रेंज में लिमिट करने की कुछ मामला होते हैं. यार ये आउट ऑफ कॉमन आ जाए, ठीक है. बैच नॉर्मलाइजेशन एक चीज़ होती है कि आप हर न्यूरॉन की आउटपुट निकाल लें, फिर सारी इनपुट नॉर्मलाइजेशन मैंने आपको बताई थी. इनपुट नॉर्मलाइजेशन क्या है? इनपुट जो फीचर्स हैं वो उनका जीरो मीन होना चाहिए और लेकिन जब आप इनपुट को आप नॉर्मलाइज कर लेते हैं आफ्टर वन लेयर, जो outputs हैं first layer की, now they are inputs for the second layer. They should be renormalized again. And that is called batch normalization. And these two things, I mean proper weight initialization and with batch normalization, this has changed the field of neural networks to deep learning. And now there are a lot of things. I mean this back propagation, all that math was there. But having a lot of layers, the layers were not acting. They were just